The closest star beyond our Sun is more than 4 light-years away. That sentence reads simply enough, but sit with it for a moment. Light, the fastest thing the universe produces, would still need over 4 full years of unbroken travel just to cover that single gap. 4 years of racing at 300,000 kilometers every second, never slowing, never pausing. And Proxima Centauri, that nearest stellar neighbor, is not some remote outpost on the edge of known territory. On the galactic scale, it is practically our next-door neighbor. Now stretch that thought outward. The Milky Way, our galaxy, just one of hundreds of billions in the observable universe, spans roughly 100,000 light-years from edge to edge. To cross it at the speed of light would take 100,000 years. Not centuries, not millennia in the plural, 100,000 years. That is longer than our species has existed in anything resembling its current form. That is the universe's cruelest trick. It fills space with stars and planets, and possibly worlds teeming with life, then places them at distances so immense that even physics' own absolute speed limit barely makes a dent in the crossing. Against that backdrop, our greatest technological achievements begin to look quietly humble. NASA's Parker Solar Probe is the fastest human-made object ever constructed. As it sweeps close to the Sun on its tight elliptical orbit, it reaches speeds of roughly 430,000 miles per hour. By any earthly standard, that is extraordinary. Faster than a bullet, faster than any aircraft, faster than any vehicle in the history of our civilization. But aim that probe at Proxima Centauri and let it run forever at full speed, and the journey would still consume thousands of years. The universe does not scale politely in response to our ambitions. Voyager 1 makes the same point with a quieter kind of stubbornness. Launched in 1977, it has been drifting through space for nearly half a century. It has outlasted careers, governments, and entire generations of people. Today it sits more than 15 billion miles from Earth, a number so enormous, it stops feeling like a number and starts feeling like an abstraction. And yet, Voyager 1 has not reached another star. It has barely entered what astronomers call interstellar space. It has not made a meaningful dent in the distance to even the nearest other sun. Half a century of continuous travel, and humanity's farthest reaching machine is still, in any cosmic sense, practically in our driveway. This is the cage humanity lives inside. Not a cage built from ignorance, and not one assembled from a lack of effort or ambition. It is a cage built from physics itself, from the sheer scale of the universe and the hard limits governing how fast anything can move through it. We have crossed oceans and climbed into orbit. We have landed on the moon and sent machines sweeping past Jupiter and Saturn and out into the dark. We have done things our ancestors would have called miracles without hesitation, but every single one of those achievements unfolded within the immediate neighborhood of one star. We have explored our front yard and called it a frontier, because the true wilderness beyond it is almost too vast to emotionally process. What makes this so particularly agonizing is that we already know the destinations are real. Since the 1990s, astronomers have confirmed thousands of exoplanets orbiting other stars. They come in every conceivable variety: scorching gas giants several times the mass of Jupiter, frozen rock worlds barely warmed by their distant suns, and the ones that capture our imagination most urgently, Earth-sized planets sitting at just the right distance from their stars for liquid water to potentially exist. Proxima Centauri b orbits the nearest stellar system to our own, just over 4 light-years away. In galactic terms, it is our next-door neighbor. In engineering terms, it remains almost entirely unreachable. The TRAPPIST-1 system, located about 40 light-years from Earth, contains 7 roughly Earth-sized worlds, several of them positioned within what astronomers call the habitable zone. Kepler 452b, described by many researchers as an Earth cousin, orbits a sun-like star and sits inside a similar habitable band. And these, are only the most famous examples from early survey work. Every passing year brings new candidates to the catalog. The galaxy likely contains billions of planets. Some may be barren and airless. Some may be wrapped in toxic atmospheres. Some may be covered in deep global oceans. And some may be worlds where life has been conducting its long chemical experiment for far longer than our own planet has existed. All of them remain behind a wall of distance so thick that they might as well be myth. Rockets, for all their elegance and genuine achievement, cannot break through that wall. Not because the people who design and build them lack imagination, they are among the most inventive engineers our species has produced. The problem is structural. Rockets are bound by a rule that becomes increasingly brutal the farther ahead you think. Moving through space requires throwing mass in the opposite direction from where you want to travel. Burn fuel, expel exhaust, ride the reaction forward. It works beautifully for reaching low Earth orbit. It works impressively for sending probes past the outer planets. But the farther and faster you want to go, the more propellant you must carry at the outset. And the more propellant you carry, the heavier the vehicle becomes. And the heavier the vehicle becomes, the more propellant it needs just to push the propellant it is already carrying. The calculation spirals into geometric absurdity. A spacecraft designed under these rules for a genuine interstellar journey becomes less like a vehicle and more like a mountain of fuel with a tiny crew compartment buried somewhere deep inside. The useful mission, the people, the instruments, the purpose becomes an almost negligible fraction of the total mass. Even the most advanced propulsion ideas we can envision do not escape this fundamental trap. Nuclear pulse engines, fusion drives, antimatter reactors. These concepts offer improvements, sometimes spectacular ones. They might cut travel time significantly, open up the outer solar system in genuinely useful ways, and push probes to small but meaningful fractions of light speed. But they all still play by the same underlying rules. They still throw mass in one direction to push a ship in the other. And the universe is simply too vast for that approach to work at the scales interstellar travel demands. Fusion powers the stars themselves, releasing energy through processes we have barely begun to harness. Antimatter converts mass into energy with a completeness that staggers the imagination. And even these extraordinary processes, applied as perfectly as physics allows, would still leave the stars separated from us by journeys measured in human generations rather than human lifetimes. You can build a stronger ore, but the ocean stays the same ocean. And then, embedded in all of this, comes Einstein. His theory of special relativity, first published in 1905, did not merely identify a speed limit. It revealed that the speed of light is a structural feature of reality itself, not an engineering barrier waiting to be overcome with sufficient cleverness. Nothing that possesses mass can be accelerated to the speed of light. As an object is pushed faster and faster, the energy required for each additional increment of speed grows without bound, becoming effectively infinite as light speed is approached. The wall does not get harder to climb. It becomes a wall that slopes upward to vertical, then past vertical into something you could not climb at all with any finite force. This is not an engineering problem. It is a feature of how the universe is structured. Relativity adds a human sting to the physical one as well. At speeds approaching a significant fraction of light, time itself begins to misbehave relative to what is left behind. Travelers, moving at near light speed, would age more slowly than people remaining on Earth. A crew that experiences a 10-year voyage might return to find decades or even centuries have passed for everyone they knew. The mission succeeds in the narrow sense of having covered the distance. It fails in every human sense. Interstellar travel under conventional physics starts to feel less like exploration and more like a permanent disconnection from civilization itself. This is the point where the nature of the question has to change. Once physicists accepted that simply building a more powerful engine could never solve the problem. Not truly, not at the scales the universe imposes. They were forced to ask a different kind of question entirely. What if the obstacle is not the ship? What if the real prison is the space between the stars? And if that is what we are actually confronting, what becomes possible when you start seriously asking whether space itself can be modified? That question has an answer hidden inside Einstein's own equations, which is the genuinely strange irony at the heart of all warp research. The same theory that forbids a ship from outrunning light does not demand that space-time itself remain static. In fact, we already know it does not. Gravity bends space-time. Massive objects cause the geometry of the universe to curve around them. The expansion of the cosmos itself carries distant galaxies away from one another at rates that can exceed light, not because anything is moving through space faster than light, but because the space between those galaxies is itself stretching. Relativity forbids faster-than-light motion through space-time. It places no such restriction on space-time changing its own shape. That distinction is the loophole. If you cannot make your ship travel faster than light through space, perhaps you can engineer space to carry the ship instead. Compress the region of space ahead of the vehicle, expand the region behind it, and the craft sits inside its own local neighborhood, while the geometry of the universe does the work of transportation. The ship is not racing. The fabric of reality is rearranging itself around the ship. Locally, inside that moving pocket of geometry, the laws of physics remain exactly what they should be. Nothing breaks relativity. Nothing violates causality in any obvious way. Globally, the journey achieves something that looks from the outside like faster-than-light travel, without actually being faster-than-light motion in the forbidden sense. Think of it through a simple image. An ant crossing an open book from one side to the other faces a long, flat journey across the full length of the pages. But a hand outside the book can fold the pages toward each other until the two endpoints nearly touch, and the ant's entire journey collapses to almost nothing. The ant has not gotten faster. The geometry of the surface has changed. The distance has been negotiated by reshaping the path rather than by accelerating the traveler. Warp travel applies this idea not to paper, but to spacetime itself. The proposal is not to push a ship harder across the universe. It is to fold the universe around the ship. In 1994, physicist Miguel Alcubierre gave this concept a precise mathematical form. His paper applied the equations of general relativity, not to describe the naturally occurring gravity of some massive object, but to deliberately engineer a specific and carefully chosen kind of spacetime geometry. What emerged from his calculations was striking: a bubble of locally flat spacetime surrounding a spacecraft. Inside that bubble, conditions would remain entirely normal. Passengers could move around freely, carry on conversations, run their equipment, and age at standard rates. The ship would never be subjected to crushing acceleration forces because it would not be accelerating through space in the conventional sense at all. Outside the bubble, space-time would be severely distorted, contracted in the direction of travel, expanded behind, the bubble itself surfing forward along that gradient, the way a wave carries a surfer without the surfer needing to swim or fight the water. What made Alcubierre's model genuinely significant was not that it proposed something wild. It was that it worked within the rules. The geometry he is as a valid solution to Einstein's field equations. The mathematics of general relativity, which already describes the bending of space-time around stars and black holes, also, when pushed in a specific direction, appears to permit something like this. Faster-than-light travel did not need to break relativity. It might instead be hidden inside it, waiting for a civilization able to read the equations carefully enough. Those equations, however, do not offer warp travel as a free gift. They offer it the way a riddle offers its answer, surrounded by conditions that initially seem impossible to satisfy. To create the required space-time distortion, Alcubierre's original model appeared to demand a form of matter with negative energy density, not antimatter, which carries positive energy, not some exotic but otherwise ordinary substance, something whose interaction with space-time curves it in the opposite direction from everything we normally observe, matter that would act like a kind of anti-gravity in a specific and carefully controlled arrangement. The amounts needed in early calculations were staggering in the most literal sense. Some estimates placed the energy requirement at a level comparable to converting the entire mass of a planet directly into usable distortion energy. The number was so large it made the problem seem less like a technical challenge and more like a cosmic joke. And yet even those numbers did not kill the research. Science is not required to accept first estimates as final verdicts, and the history of physics is full of examples where the initial energy costs of a new idea were dramatically revised as understanding deepened. Researchers began adjusting the geometry of the proposed bubble, changing its thickness, refining the shape of the distortion field. Something unexpected happened. The energy requirements began to fall, not to practical levels, nothing remotely close to what any existing or foreseeable technology could generate, but the direction of change mattered enormously. The problem changed its emotional character. It stopped being an absolute impossibility and started looking like an extraordinarily demanding engineering challenge. A challenge, however severe, invites continued effort. An impossibility does not. This is where Harold White and related experimental work became part of the conversation. Working within research programs connected to NASA and later through independent avenues, White and colleagues asked whether a more mathematically refined bubble geometry could reduce the energy demands further. More importantly, they began asking whether any aspect of warp-like physics could be brought into the laboratory at all, not to build a propulsion system, but to see whether the underlying physics could be engaged at measurable scales. If even a microscopic, embryonic version of a warp-like space-time distortion could be created and verified, it would represent something qualitatively new, a connection between the theoretical framework and experimental reality. This line of investigation connects directly to one of the most counterintuitive discoveries of modern physics: the vacuum. The emptiness of space between particles, between planets, between stars is not truly empty. Quantum mechanics reveals that even a perfect vacuum is alive, with ceaseless activity operating at scales too small for ordinary perception but entirely real within the quantum framework. Particle-antiparticle pairs flicker in and out of existence. Energy levels in the vacuum fluctuate constantly. The void is not a passive absence. It is a dynamic medium with hidden structure, more like a restless ocean beneath a dark surface than a clean mathematical zero. The Casimir effect makes this concrete and measurable. When two metal plates are placed extremely close together in a vacuum, close enough that only certain wavelengths of quantum fluctuation can exist in the confined space between them. The plates are pushed toward each other by a measurable force. No magnet, no field, no visible mechanism acts on them. The quantum vacuum simply behaves differently inside that narrow gap than it does in open space around the plates, and that asymmetry generates a real, detectable pressure. This has been confirmed experimentally numerous times. The vacuum is not neutral. Under the right geometric conditions, it can be influenced and manipulated, however modestly. For warp research, the significance of this is not that the Casimir effect constitutes a propulsion mechanism. It clearly does not, at any scale remotely relevant to transportation. The significance is that the vocabulary of warp physics and the vocabulary of measurable laboratory quantum reality are not entirely disconnected. The idea that space-time conditions could be influenced by carefully engineering the local quantum environment shifts from being a purely abstract theoretical aspiration to something with at least a distant physical basis. The gap between current capability and useful warp-like distortion remains enormous, but it is a gap between two real things rather than a gap between a real thing and pure fantasy. White's team eventually described experimental results suggesting that small warp-like space-time structures might have appeared within laboratory instruments under specific and carefully prepared conditions. The public response was intense, and the scientific response was appropriately skeptical. The structures in question, if they were real and not instrumental artifacts, were so minuscule as to be almost beyond description. Operating at these scales is extraordinarily difficult, and the difference between a genuine physical signal and a sophisticated form of measurement noise can be nearly impossible to establish definitively without extensive replication. The caution was not merely conventional scientific conservatism, it was essential, because extraordinary claims in a field this charged with cultural and popular meaning require correspondingly extraordinary rigor. With that caution fully acknowledged, something genuine had still shifted. Warp-like space-time effects were no longer discussed solely in the language of theoretical physics papers. They had entered the language of experiment, however tentatively and however disputed. That crossing of a threshold has consequences. More researchers direct attention to the area. Better instruments get proposed and built. New mathematical approaches are tested. Disputed results attract the kind of intense scrutiny that science is best at applying. The subject had accumulated just enough physical substance to survive in serious scientific conversations, and that survival creates its own forward momentum. The research also opened an unexpected perspective, extending far beyond our own future plans. If a warp bubble could genuinely move through space, it would create a disturbance in spacetime's geometry, unlike any naturally occurring source we already know how to classify. Gravitational waves have already demonstrated that spacetime carries information across cosmic distances. When two black holes spiral together and merge when neutron stars collide in catastrophic violence, the event sends ripples outward through the fabric of reality at the speed of light, and instruments like LIGO can detect those ripples even from billions of light years away. We have already learned to listen to the universe, speaking in the language of space-time geometry. Some researchers began asking an unsettling follow-on question. If an advanced civilization elsewhere in the galaxy has already achieved warp-capable travel, would its ships produce a distinctive gravitational signature, a pattern of space-time distortion unlike any known natural phenomenon? A moving warp bubble would be a traveling deformation in geometry. It might have a recognizable fingerprint, a specific pattern of compression and expansion that would look nothing like colliding stars or merging neutron stars or any other event in our existing catalog. If such a signature existed in our data, and if we developed the sensitivity and theoretical framework to recognize it, then warp research would expand from a question about our own future into a question about the present state of the galaxy. No confirmed signal of this kind has been identified. The sky has not yet announced that someone solved the problem before us, but the mere act of searching changes what warp technology means. It becomes both a goal and a lens, a way of asking not only where we might go, but whether intelligence elsewhere is already going there. Step back from the equations and the experimental results for a moment and consider what a genuine breakthrough in this direction would mean for the human story at its largest scale. Every human being who has ever lived, every city and monument and library and language our species has produced, every scientific achievement and cultural tradition and personal memory, all of it is located on a single planet orbiting a single ordinary star in an unremarkable region of one galaxy. We speak about civilizational risk in careful, measured language, but what we are really describing is a species with no backup copy. Everything we are and everything we have become exists at one address, and that address is not guaranteed safe across the timescales the universe operates on. Asteroids do not negotiate. Stellar evolution does not pause for intelligent life. A species confined to one world is a species living without redundancy in a universe that has proven repeatedly capable of dramatic, sudden, and irreversible change. Warp travel would transform that condition in the most fundamental way possible. If nearby stellar systems become reachable within human lifetimes rather than across human generations, then other worlds cease to be abstract entries in a telescope archive and become actual places, destinations with gravity and weather and geology and atmosphere, shores that living human beings might stand on. The night sky would stop being a ceiling above an enclosed space and become the visible portion of a network of connected places. Children growing up in a civilization with warp-capable ships would have a relationship with the universe that is simply unrecognizable compared to our own. Not metaphorically enlarged, but practically, concretely different. The scientific consequences alone would be transformative at a level that makes current astronomy look like a prelude. Direct access to exoplanets would revolutionize biology, geology, atmospheric science, chemistry, and the search for life beyond Earth simultaneously. We would stop inferring the properties of other worlds from the shadows they cast across their stars and start measuring them directly. Is biological evolution convergent? Does it tend toward similar solutions under similar conditions, producing things recognizable even from alien chemistry? Or does life on different worlds look so completely unlike our own examples that our existing categories of classification collapse entirely? Do planetary processes like plate tectonics and volcanic activity play out differently under different gravitational conditions and different internal heat profiles? Can life arise and sustain itself in chemical environments radically different from the carbon and water framework we know? These questions, currently theoretical at best, would become empirical. We would stop constructing plausible answers and start accumulating actual data from worlds shaped under conditions Earth never experienced. The economic transformation that would follow operates on a different timeline but with no less force. Every major navigational revolution in recorded human history has redistributed power and reshaped civilization. Sea routes built empires. Railways restructured continents. Air travel compressed the globe until distant events became immediate. Warp travel would do something beyond all of those. It would convert the galaxy itself into an economic landscape accessible to human effort. Resources distributed across billions of stellar systems, materials, energy sources, and substances unknown to our current industries would shift from abstraction to competition. The civilization that develops warp capability first would not merely gain a transportation advantage. It would gain a structural and strategic position so overwhelming that nothing in recorded history provides an adequate comparison. This is why the subject carries ethical weight alongside its scientific and engineering dimensions. Who controls access to warp-capable travel? Who decides which worlds are approached, studied, settled, or exploited? If life exists on an otherwise promising planet, even microbial life, even simple chemistry not yet recognizable as an organism, what claim does it have against a species with faster-than-light ships and resource needs? If intelligent life exists beyond Earth, then warp technology becomes not just transportation, but the foundation of contact and diplomacy between civilizations at interstellar scale. Humanity has never practiced anything remotely like that. These questions do not have answers yet, but they are part of the technology itself, embedded in what happens when the capability becomes real. The psychological transformation may ultimately be the most profound and the hardest to anticipate. A species that knows it can reach the stars is not the same species that merely looks at them from a single planet. There is a difference that runs very deep between living beneath a ceiling and living at the edge of a genuine horizon. Throughout most of history, the stars were lights, beautiful, mysterious, inspiring of mythology and wonder, but not inviting plans. They were objects of contemplation, not destinations for consideration. Warp travel converts them from symbols into places. And a species that can make concrete plans about real places has a fundamentally different orientation toward the cosmos than one that can only look upward and feel the distance. None of this can be presented responsibly without acknowledging the actual state of the research with full honesty. The gap between where warp physics stands today and a working propulsion system is not a gap measured in years. It may not even be a gap measurable in decades. The energy requirements, even in their most optimistic revised forms following geometric refinements to the bubble models, remain so far beyond anything our civilization currently produces or can plausibly envision producing in any near future that the comparison is almost uncomfortable to state. The exotic matter or engineered vacuum conditions that various models require may prove far more difficult to create at useful scales than current experiments suggest. There may be fundamental stability problems with warp bubble geometries that make practical application impossible even in principle. There may be deeper issues with causality. Warp-capable travel might allow, at least in theory, the construction of closed time-like curves, loops in time that the universe may have some deeper mechanism for preventing, a kind of cosmic enforcement of its own consistency. None of these problems have been solved. Several have not been fully understood. The field is early, disputed in many of its specific claims, and surrounded by the legitimate uncertainty that always attaches to genuine frontier science. What has changed is not the distance to the goal. What has changed is the direction and character of the question being asked. For most of history, the question was whether our engines could be made fast enough. That question had a discouraging answer that did not improve with time or effort. The new question is whether space-time itself can be engineered to make distance negotiable. That is a different kind of question, and its answer remains genuinely unknown. Not answered negatively, not answered positively. Unknown, and that unknowing, in science, is precisely the condition that invites serious investigation. Science progresses not only by confirming what is possible, but by dissolving what was assumed to be fixed. The atom was once considered the indivisible limit of matter. Black holes were once abstract mathematical results that serious physicists doubted would ever be physically real. Gravitational waves were once predicted to be too faint to ever detect with any instrument conceivable within the laws of physics. Each of these apparent limits eventually gave way, not because ambition overran physics, but because careful study found that the supposed limit was never as absolute as the first understanding suggested. The bars of the cage turned out to be less solid than they had appeared. Warp research lives in a stage now that is recognizable from those earlier histories. The bars of this particular cage are being examined with real instruments, real equations, and real scientific rigor for what is essentially the first time. The verdict is not in, the case has not been decided. It may turn out that nature allows warp-like distortions only at scales so tiny they can never become propulsion, a door that opens a crack and refuses to open further. It may turn out that there are layers of physics deeper than our current understanding that close the loophole just when it seems about to widen into something useful. That possibility is real and should be taken seriously. But there is also the other possibility, that the opening is genuine, that the asymmetry in how space-time can be shaped is not merely a mathematical curiosity, but a physical fact with engineering consequences, that the conditions required, though extreme by any current measure, belong to the category of things that are very difficult rather than the category of things that are truly forbidden. That somewhere ahead in the work, not close, not easy, perhaps not reachable in any single lifetime of research, there is a configuration of matter and energy and geometry that carries a ship across the void the way a current carries a leaf across water. If that possibility is real, then everything about the long-term future of intelligence in this universe changes. Not quickly, not smoothly, not without struggle and failure and revision and discovery, but directionally and permanently. The stars would stop being destinations reserved for hypothetical descendants and begin, however slowly, to become places. Real places with real shores and real skies and real conditions that no human eye has yet seen. That is enough to change the shape of the future. It is enough to fund the laboratories and run the calculations and argue over the data. Because, throughout the long history of things that turned out to be possible after all, a consistent pattern appears. The revolution never looked like a revolution from the inside. It looked small, uncertain, and easy to dismiss, until one day it did not. Warp research lives in that interval now, not proven, not abandoned, investigated. And that, perhaps more than any specific result, is the most important thing to understand about where this idea stands and why it refuses, despite every obstacle, to go away.